StickMan Physics video on refraction and Snell's law. Before we get too much further, make sure that your calculator is in degrees. So if you hit mode and then degrees, you can get it into degrees. Since we'll be using sine and inverse sine, it's going to be important for your calculations to be accurate. And we're going to be looking at the phenomenon called refraction. Refraction is a bending that is created from when you go from one medium to another, and the speed of light changes in that one medium versus another. The speed of light's faster in air than it would be in water. The units we're going to use are in this table. If you go to our site, you can look at it a little closer, but C being the speed of light's a big one, we're going to see a couple places. This number will always be 3 times 10 to the 8th meters per second because it's the speed of light in a vacuum. Whereas V in this unit, we're going to talk about velocity of light. It's going to be something else probably, unless we're talking about the velocity in a vacuum, which would be 3 times 10 to the 8th. But you'll see that a little bit later. Index of refraction, if there's only one index of refraction because you're just traveling through air, you're going to just use n. Later on, when we go from one medium to another, we're going to have an instant, a starting side, and an ending side. So we're going to have to specify with a subscript I next to the end. So that's the instant side or refracted side you'll see later on. And then the same thing going, we're going to have an angle that's going to occur on one side and on the other, so you'll have incident and refracted. You'll see that later on. Okay, just reminding you about electromagnetic waves. They like to travel through vacuums. They're going to travel fastest with no particles, and as the density of the material, like gas or liquid or solid, increases, they're going to start going slower and slower and slower. And within solids, the density is going to also matter. And we're going to look at different materials that end up being translucent. Translucent just means you can see through it. If you can't see through it, you're not going to get light traveling through there. And then there's going to be this value called index of refraction, a variable n, that just relates to the speed of light in a medium, how fast it's really going. Because if it's going in a medium other than space, air is going to be pretty close. A vacuum of space or air, we're going to have a number that's going to be, might be substantially higher than 1. Okay, so this is the equation for index of refraction. It's n equals c over v. N stands for index of refraction, c stands for the speed of light, and this value c is always going to be the same thing. It's going to be 3 times 10 to the 8th, and v is the speed of light in the medium, whatever it's traveling in. And so this equation right here pretty much can always really start at 3.0 times 10 to the 8th over a velocity, because that c is never going to change. So we just write it as c because it's just a constant. But if you plug it in every time, you can start from here. Another thing about index of refraction, has no unit because this is going to be meters per second, and this is going to end up being meters per second, so it cancels itself out. And the last thing is this cannot be bigger than the velocity of light. It has to be smaller. So as this gets smaller, the n value gets bigger. So the bigger the n, the slower. So just realize that what that relates to. If you have a big, and we'll look at it in a second. Let's take a look. After we do this, we're going to go ahead and just rearrange this equation real quick. If you're solving for velocity, what you're going to end up doing, you will end up multiplying out the velocity to get it into the numerator, and so that ends up being Vn equals c. And now if we want to go ahead and get just v alone, we want to divide out n. And so what happens is that this equation would have changed to v equals c over n if you ever had to solve for velocity of light in a different medium other than the space, where it would travel at the 3 times 10 to the 8th, which is c. Looking at this, so going with what I said before, the bigger numbers, this is going to be the slowest. Smaller numbers, this is going to be the fastest. And within materials, density is going to matter too. Within a solid, light's going to travel at different speeds. So here's your first question. What's the speed of light? V equals question mark. That has an index of refraction, so it has an n of 1.333. And we know this is a given. It's on your equation sheet if you have an equation sheet from my class. But it's going to be always, go back, 3 times 10 to the 8th meters per second. So we're solving for speed of light, rearranged equation, v equals c over n, c being 3.0 times 10 to the 8th, and n being 1.333. 3, and if we do the math, V equals, so 3 second E8, that's how I enter it in my calculator, divided by 1.333, and I get a big old number, 225056264.1. Well, I'm gonna round that, and I'm gonna go ahead and use scientific notation, and that's gonna end up being 2.25 times 10. We're trying to figure out to what. We have to look at all the jumps. So 1, 2, 3, 4, 5, 6, 7, 8. It's going to be 2.25 times 10 to the 8th meters per second. It'll be a little clearer if you go to our webpage, and you'll see the solutions. When you click on see solution on these different problems, you'll see a little bit better than my handwriting, but it goes with what I'm going through right now. Okay, what's the speed of light in diamond? V equals question mark. In diamond, it has index of refraction of 2.419, and C, once again, is always going to be that constant, 3 times 10 to the 8th. And so, solving for V equals C over N. V equals 3.0 times 10 to the 8th over 2.419. So 3 second E8 divided by 2.4419. And you get 124018189.3, and I'm going to round that to 1.24 times 10 to the 8th meters per second. Once again, 1, 2, 3, 4, 5, 6, 7, 8. That gives you this number right here, that 8. So that's not negative, that's just an 8. 1.24 times 10 to the 8th meters per second is our answer for this problem. What's the index of refraction? So now we're solving for N, that for ice at 20 degrees Celsius. This is not going to matter here. And we don't need it here. Where light travels at 2.29, so light is not traveling at C. 2.29 times 10 to the 8th meters per second. We still need C. 3.0 times 10 to the 8th. And we do the math. N equals C over V. N equals 3.0 times 10 to the 8th over 2.29 times 10 to the 8th. And we get 3 second E8 divided by, use parentheses, some of you might type numbers in differently, 2.29 second E8, close parentheses, and I get N equals 1.31, and so there's your answer. Does light travel faster in diamond with an index of refraction of 2.419 or cubic zirconia with 2.20 with an N of 2.20? So which one is going to be faster? Well, the one that's faster is going to be one, though, the N value that's lower or smaller. And so in this case, it's going to be the 2.20, which is cubic zirconia, is going to be the answer here. Okay, so now we're going to go into Snell's law, and that's going to involve two medium. You're going to have either a slower medium here and a faster medium there, or a faster medium here and a slower medium there. And this diagram itself can be drawn many different. Like right now, I have the boundary. So you have some sort of medium here, and then all of a sudden light's traveling into a new medium, and when it gets into this new medium, it's going to get a little faster. And that's going to cause a bending. It's going to cause a bending outwards. So just a reminder from a previous lesson, if you're traveling slower in the new medium, so in this case that's not what's happening, you're going to bend towards the normal line. If you're traveling faster in the new medium, which is what's happening here, you're going to bend away from the normal line. And just to go with some of the definitions, normal line is this line right here down the middle, and it's just going to be a 90-degree angle to the boundary. That's where we draw it. And since it's refraction, we're going to draw it through. So you notice how the dotted line is going all the way through, past into the new medium. And that's going to give us a couple other things. It's going to give us the angle of incidence on this side. It's going to give us the angle of refraction on this side. And it's always going to be, these things are always going to be relative to the normal line. So when we're putting in values, it's going to be based on how far it is from this, the angle is from this. And then we're going to have, since we have two mediums, we're now going to have subscripts. Incident means starting. So this is the incident wave, and this is going to be, because it's refracting over here, it's going to be the refracted wave. And what I'm not showing you is there actually would be a reflection going on in this picture too. I just left it out. That would just go with the law of reflections, where this side would be equal to that side. But if you're going from a slower to faster medium, the angle of refraction is always going to be different than the angle of incidence. Okay, so slower medium to faster medium, you are going to, first of all, bigger values mean slower, because this one is smaller. The smaller the value, the faster. And so therefore, we're going to end up bending, as we go through the medium, we're going to end up having a slight bend outwards. And so this angle right here is going to be bigger because light's traveling faster in this new medium. Faster medium to slower medium in this case. Now we have faster because this is going to be faster because this is less. So n is less. And so therefore we're going to have a bending, and this is going to be towards normal line. So it's kind of bending inwards as it goes into the new medium. So we're using subscripts here. I said that earlier. The incident and the refracted side, incident being the starting, refracted being where it's going. There's your different variables you have, and it's going to be useful to draw a quick picture and just put your givens in a picture as you answer questions. And so I'm going to draw a picture that looks something like this. I might not shade the other side, but I'll draw a picture like this before I answer questions. Also, with rearranging the equation, if you're ever rearranging the equation for n's, you're going to have to divide out the other sine angle I, put it on that side. So if you're solving for ni, it ends up being this right here. If you're solving for nr, you're going to have to get rid of the sine angle r. You divide that out, and it ends up being here. Now, one other thing is, if you're ever solving for one of these angles, which we're often solving for the refracted angle, what we're going to have to do first, and let me just go ahead and write this out, ni sine angle I equals nr sine angle r. And what we're going to have to do first is we're going to have to divide out the nr to get rid of it. So we divide both sides by nr. But then we're going to have to do this inverse sine. So we're going to have to take this side and we're going to have to go sine angle inverse. And that's going to get rid of this. But while it gets rid of that, it's going to put an inverse sine over here, and this whole value is going to be inverse. And so that's where we get the angle r, which is right here. That's how we get this equation. So angle r equals inverse sine ni sine angle I over nr. Just some tips. Make sure we're doing Snell's law. Use extra parentheses. We're going to have a lot of numbers in here. Also, if you're ever taking the inverse sine, make sure you probably have a calculator mode where you have to take the inverse, like second. There's a sine button. You might have to take second sine or do something like that. But you should have, if you're solving for an angle, you're going to be using inverse sine a couple times. You might still be using this too, but you're going to be using the inverse sine. So make sure you're typing in the right one. Also, make sure your calculator's in degrees. If you're getting problems wrong, this is one big thing. Anytime you have a trig function, you have to know what you're working with. And in physics, so far, we've just been working in degrees. So anytime you see sine, cosine, tangent, inverse sine, inverse tangent, whatever, you're gonna have to make sure your mode is in degrees. So check that. A lot of calculators will be in radians if it's a graphing calculator. If it's not a graphing calculator, it's probably already in degrees. And just keep on using parentheses. Keep everything where you need it to be. So that will help get the questions right. So let's take a look before we do the math. Will light bend towards or away from the normal line when going from a slower medium to a faster medium? So if it's going from a slower medium to a faster medium, it is going to bend away. Will light bend towards or away from the normal line when going from air to water? Well, now we have to look at this and we have to decide. We're making this the last question. Well, which one's faster? This is faster. The smaller number. This is slower. It's a smaller n value. So we're really going from a faster to slower medium, and when that happens, we're going to bend toward the normal line. Okay, then we get into some Snell's law problems. What's the angle of refraction? So we're asked for what's the angle r? I'm going to go ahead and draw a picture, and I'm going to draw it differently. I'm going to go ahead and draw, just so you see that it doesn't really matter. I'm going to draw the boundary here, and I'm going to draw the dotted line here. So there's your normal line, and we're going to have light coming in, and I'm not going to worry about the bending right now. I'm just going to draw this through, and I'm going to angle this side, angle r, and it tells me that this angle is 20 degrees. And then it tells me also you're going from air, so this side, which is the incident side, Ni equals 1.00, and we're going into water, where you have a, again, it's not up here because I drew the boundary right there, you're going to have the Nr equal 1.33. So everything on this side right here is going to have an index of refraction of 1.33. And then our angle we're looking for, we're going to have to solve for, this is angle I. We're going to be solving for the angle of refraction right here, and that's what we're trying to solve for. So here's our givens list. We have angle I, 20 degrees, Ni, 1 degree, 1, just 1. Angle R, we're trying to find that. Nr is going to be 1.33. So we rearrange our equation. Angle R equals, and if you remember from earlier, it's going to be inverse sine of Ni sine angle I. And that's going to be over Nr. And that would be Nr. So putting in the numbers, inverse sine, Ni was 1, sine 20 degrees, and that's all going to be over 1.33. This is where extra parentheses will be useful, just to have everything. I like to type in this number first. So I'll type in 1, even though I don't have to type in 1 because 1 times anything is 1, times sine, I'll put 20, I'll hit enter, get into my calculator, I see 0.342, something, something. I'm going to divide that by 1.33. At this point in time, I see 0.257158. Well, I'm not done yet. I'm going to go ahead and take the inverse sine of it. So I find that second button in my sine button to get an inverse sine. And with my calculator, I could just hit second and answer and pull that last answer back in. And when I do that, I get an angle of refraction of 14.9. Let's see if it works itself out. I'm going from a faster medium to slower medium, so I'm going to bend towards normal line, and this angle should be less than that angle, which works itself out. Okay, what's the angle of incidence when the angle of refraction is 15 degrees? So I'm just going to draw this picture again. I'm going to draw just a line through. My angle of incidence is unknown. The angle of refraction is 15 degrees. I'm going from this side, the Ni, the incident side is 2.42, and I'm going into a refracted medium, new medium, where it's going to bend, and the index of refraction here is 1.33. So I'm solving for angle I, and when I rearrange that equation, I'm going to get inverse sine. Once again, anytime you have an angle, you're going to have an inverse sine when you're using Snell's law. Inverse sine of the whole value, Nr sine angle R, over Ni. And so just writing out the numbers, inverse sine of Nr, which is 1.33 times sine of 15 over the Ni of 2.42. So I'll type that into my calculator. Once again, I like to do things backwards. 1.33 times sine 15 equals, I see 0.34422. I'm going to divide that by 2.42. I'm going to get my answer. I see 0.14224 right now. And I'm going to take the second sign to get the inverse sine, second answer to pull in the answer, hit enter, and I end up getting an angle of incidence of 8.1, let's go with 8. 8.17769, but 8.18 degrees, and let's make sure it works. We're going from a slower medium to a faster medium, so we should end up having less, because our angle is going to increase as you go into faster medium. So this should be less, and it is less. 8.18 is less because it was a slower medium, the angle here. What's the index of refraction for unknown substance when the angle of incidence is? So we'll just draw a picture again. We got a ray going through. We have an angle of incidence, once again on the inside of closest to the normal line, of 20 degrees. and it's in air, traveling in air, so we're going to give this an I, and it's going to travel into this unknown substance where it's going to bend, and it's going to bend, looks like it's going to get slower because it's going to bend towards the normal line. So we're going to solve for nr, and we're going to expect this number, because it's slower, to be a bigger value than that 1 right there. So let's try this out. nr equals, and here we're going to have ni sine angle I over sine angle r. So nr equals ni, which is 1, times sine of the angle I, which is 20 degrees right here, over sine of 15 degrees. Notice how when we're not solving for an angle, we have just sines in our problem. So 1 times sine 20, I get 0.34202, and then I divide that by, open parentheses, even though I don't really have to do this, but I want to keep everything together, just in case you don't know. It's just good to have extra parentheses. Sine 15, close parentheses, and I get 1.32. And so my index of refraction on the refracted side of this unknown substance is 1.32. And so it's bigger because it bends towards. So my picture is not to scale since it looks straight, but I just draw a straight picture and then I solve for it and I figure out what way the bending would have been because of this. Okay, what's the angle of refraction for unknown substance when the angle of incidence is 31 degrees unknown angle to the unknown angle, and the angle of refraction is 26 degrees in water? So I'm just trying to do every problem every single kind of way you can do this. Light's coming through. What's the index of refraction for unknown substance here? Angle of incidence is equal to 31 degrees. Angle of refraction is equal to 26 degrees. And it's going into the unknown, so it's going from an ni of 1.33 to an nr of what we're trying to solve for. So we're solving for nr, so nr equals, divide the sign out to get it on the other side, ni sine angle I over sine angle r. We do the math, nr equals, the ni was 1.33, sine of 31 degrees, over sine of 26 degrees over here. And we do the math, 1.33 times sine of 31 equals, I see 0.685 right now in my calculator. I divide that by, open parentheses, sine 26, close parentheses, twice, and I get nr equals 1.5626, but I'm just going to stop at that, 1.56. So what's happening is light is bending. This is less. So light's bending. This is more right here. So as light gets through, it's bending towards the normal line, so I would expect this value to be slightly higher, which it is. So I'm kind of checking my work as I go. Total internal reflection only works when you're going from a slower medium to a faster medium. And what happens is, take a look at this ray right here, as the refracted ray bends away from the normal line, there's going to be some point where the angle of incidence doesn't matter. It can get as big as it wants, and there's only going to be refraction. So here's a definition of total internal reflection. When light no longer reflects into a new medium, only there's a reflection. Critical angle is the angle of incidence after which light will only reflect and not refract. So they kind of work together. At the critical angle, there's only going to be total internal reflection and no refraction left over. And it's also only going to occur from a slow to a fast medium. It will never occur from a fast to a slow medium because of the way that the bending occurs. What is the critical angle for light and diamond going from 2.42 to air 1.0? Well, you're going to go ahead and use the equation. Angle C equals sine inverse sine of nr. In this case, when you're trying to decide which one is the nr, it always has to go from slower. So this number down here is always going to be bigger to faster. And so anytime if it's possible to have a critical angle, it has to be from slower to faster. The number down the bottom is always going to be bigger. 2.42 to 1. And so if I take inverse sine, second sine, open parentheses, 1 divided by 2.42, close parentheses, equals, and I get 24.4 degrees. Anything past 24.4 degrees, you're not going to have any more, you're not going to have a refraction. And your calculator will actually give you an error. If you did this and you put the 2.42 above the 1, you get an error, and your calculator wouldn't give you the right value. So you pretty much are worry-free that either you're going to get an error or you're going to do it right. And it will always be the faster or the smaller end value over the bigger or the slow end value. Hope that helped. There's a little animation or a simulation you can do with the PhET lab at the very bottom of our page. Take a look at it. There's this picture right here that gives you some information on how to do the lab. You'll see a link where you can download a mini lab and go through it. And if you're in my class, I expect you to do that, and you get a little extra credit on the next assignment. Have a good one. Bye.